Welcome everyone. This is part B of section 10.2. It is calculus with parametric curves. So last video, part A of the video of 10.2, we saw when how to find the slope of the tangent to a parametric curve, and then what do you mean by horizontal tangent and vertical tangent? What are the conditions for that? How to take the second derivative. And we also saw an example to find the tangent line of a cycloid. Now the next topic is areas, which are for parametric curves. How do you find the area? So before we actually get into this concept, from Calc 1 class, you know that if you have a curve, um, f of x, bounded by the lines x equal to a and x equal to b, then the area under this curve bounded by x equal to a and x equal to b is given by the definite integral a to b fx dx. Or in short, you can also write, if you consider y as a function of x, then it can be written as y dx. So keep this in mind. Now we are going to extend this idea to parametric curve. We know that the area under the graph y equal to f of x from a to b is a equal to integral a to b fx dx, where f of x is more than or equal to 0. If the curve is traced out once by the parametric equations, x equal to f of t and y equal to g of t, where t lies between alpha and beta, then we can calculate an area formula by using the substitution rule for definite integrals as follows. A is integral a to b y dx, which is integral a to b, or integral alpha to beta, because we are converting everything to t, the variable t. Y is a function of t, which is equal to g of t, and x is f of t. When you do dx, it will be f prime t dt. That is dx, f prime t dt. So it is alpha to beta g of t f prime t dt. So area formula in parametric form takes up this representation. In order to remember this, even if you remember this, you can always convert that to parametric. A equal to integral a to b y dx is what you want to remember. Example, find the area under one arch of the cycloid x equal to r times theta minus sine theta, y equal to r times theta 1 r times 1 minus cosine theta. So when you consider one arch of the cycloid, we are finding the area of this part. So let's write down the area formula. Area is integral 0 to 2 pi, or because we are talking about x and y, so it's y dx. So if we write the variation for x, it is from 0, it is from this position to this position. So it is x is from 0 to 2 pi r. Now we are converting that to t now. So it becomes 0 through 2 pi. So you are rotating a coin once. So that will be through an angle of 2 pi, 0 through 2 pi. So theta becomes 2 pi here. For that variable, you are going to substitute for y. Y from here is r times 1 minus cosine theta. Then you're going to do dx from here. Dx equal to r times 1 minus cosine theta d theta. So if you differentiate or you take the differential of x, so that will be r times 1 minus cosine theta d theta. So this is d of x. And this is the part we want to integrate. If we reduce this, it is integral 2 pi. R square is a constant, and you get 1 minus cosine theta the whole square d theta. So it is area equal to R square, which can be taken out of the integral sign being a constant. Integral 0 through 2 pi, 1 minus 2 cosine theta plus cosine square theta d theta, if you expand this in binomial. So area equal to R square. These two can be integrated. The first two terms can be integrated easily. So which is going to be theta minus 2 theta minus 2 times sine of theta between theta equal to 0 through 2 pi. Then you are going to integrate 0 to 2 pi. Of course, you have that R square outside. Cosine square theta by Pythagorean identity, by trigonometric identity, this can be written as 1 plus cosine of 2 theta over 2. We have seen this type of integration in chapter 7 when we did techniques of integration. Whenever you find a sine or cosine in terms of even power, then you have to use double angle formula. This is trig ID. So it is R square, A equal to R square. And then you're going to substitute the upper limit, which is 2 pi minus 2 times sine pi, then sine 2 pi. Then the lower limits, everything becomes 0. Then you have R square over 2. What you're doing is you are bringing the 2 outside. And then you integrate, which is integral of 1, that will be theta. Integral of cosine 2 theta, that would be sine 2 theta over 2 between 0 and 2 pi. So it is sine 2 pi part is 0. So it is R square times 2 pi plus R square over 2. Then you're going to substitute the upper limit. Upper limit is 2 pi. Then the upper limit sine of 2 times 2 pi would be sine of 4 pi. That would be 0. The rest of the values would be 0. So here you're going to cross these out. So you are left with 2 pi r square plus pi r square. That will be 3 pi r square. We'll see how to find the arc length for a parametric curve. So in chapter 8, we have seen arc length formula as L equal to integral a to b square root of 1 plus dy by dx the whole square dx. This is from chapter 8. When C is a curve, y equal to f of x lying between a to b. So in order to get the length of the curve, we used this formula. We have to modify this for parametric curve. We know that C can also be described in parametric form as x equal to f of t, y equal to g of t, where t lies between alpha and beta, where dx by dt is f prime t. This means that C is traversed once from left to right as t increases from alpha to beta. Then the initial point A would be f of alpha. The final point B for x would be f of beta in terms of t, x and y changing to x and y changing to f of alpha and f of beta for x of t and y of t. Putting this in this formula, we get L equal to integral a to b square root of 1 plus dy by dx the whole square dx, and this part becomes, we are going to change this whole thing to parametric. So it is integral alpha to a to b becomes alpha to beta, then square root of 1 plus dy by dt the whole square by dx by dt the whole square, because dy by dx is dy by dt over dx by dt times we want to change this dx and write this in terms of parametric, and we will do manipulate like this dx by dt times dt. So if you take the common factors out, if you take the common denominator, and this would become integral alpha to beta, and integral square root of dx by dt the whole square plus dy by dt the whole square, all divided by the whole thing divided by dx by dt the whole square within the radical. So if you take the radical out, it is dx by dt below. There is one more dx by dt on the numerator. Those two get cancelled out. So this and this get cancelled out. So ultimately, when dx by dt is positive, and dx by dt is positive, you get L equal to the formula integral alpha to beta square root of dx by dt the whole square plus dy by dt the whole square dt. So that is the modification that you would make from chapter 8 to chapter 10. Chapter 8 is in Cartesian, for the Cartesian curve, how to find the length of the curve. And chapter 10 is about parametric curve when x and y are written in terms of the parameter t and how to find the arc length. So we state that as a theorem. If a curve C is described by the parametric equations x equal to f of t and y equal to g of t and t lies between alpha and beta, where f prime and g prime are continuous on the closed interval alpha beta, and C is traversed exactly once as t increases from alpha to beta, then the length of C is L equal to integral alpha to beta square root of dx over dt the whole square plus dy over dt the whole square dt. Uh, we will we will use this result for the example 4. Use the representation of the unit circle x equal to cosine t, y equal to sine t, t lies between 0 and 2 pi to find L. Use the representation of unit circle for x equal to cosine t, y equal to sine 2t, where t lies between 0 and 2 pi to find the length L. So we have done these two problems. We have actually drawn these two parametric curves in section 1. Refer to those two problems where we have sketched the two graphs, one corresponding to the first one, second one also we have drawn those two graphs. Please refer those. One will be traversed only once, the first one. The second will be traversed. It's also a circle. Both of them are circle, but it'll be traversed twice in the second part, in part B of this. So let's see what change does it make in terms of length. Okay, so length of the curve for part A. So L equal to integral alpha to beta. It's given in the problem, it's 0 to 2 pi, square root of dx over dt, the whole square, plus dy over dt, the whole square, dt. So we know that x equal to cosine of t. So dx by dt equal to negative sine of t, y equal to sine of t. So dy by dt equal to cosine of t. So if you apply that over here, it is integral 0 through 2 pi square root of integral 0 to 2 pi square root of dx by dt, which is negative sine t, the whole square, plus um, cosine of t, the whole square, dt. That is integral 0 to 2 pi. That is square root of sine square t plus cosine square t. By Pythagorean identity, it is 1. So integral 0 to 2 pi 1 dt, which is equal to 2 pi. So for part A, the length of the curve is nothing but the circumference of the circle whose radius is 1, because it is unit circle. Unit circle means the radius of the circle is 1. So it is 2 pi r, r equal to 1. So we get L equal to 2 pi for part A. So let's see part B. The same formula, L equal to integral 0 to 2 pi square root of dx by dt the whole square plus dy by dt the whole square dt. X is given by cosine of 2t and y is given by sine of 2t. So dx by dt would be, so you have to apply chain rule. So outer derivative times inner derivative. Outer is cosine derivative, that is negative sine. Inner is 2, so it becomes negative 2 sine of 2t. Then dy by dt would be 2 cosine of 2t. So if you substitute that in this integral, it's integral 0 to 2 pi, square root of negative 2 sine of 2t the whole square plus dy by dt, which is 2 cosine of 2t the whole square dt, which is integral 0 to 2 pi square root of 4 times sine square 2t plus 4 cosine square 2t dt. So you can take 4 as a common factor out. That is integral 0 to 2 pi square root of 4 times sine square 2t plus cosine square 2t dt. By Pythagorean identity, and this part is equal to 1. So it is just integral square root of 4. So it is integral 0 through 2 pi. Square root of 4 is a 2. So 2 dt. That is 2 can be taken out. Integral of 1. So it is 3. That is upper limit minus lower limit. It's 2 pi minus 0, which is 4 pi. So length of the curve in this case equal to 4 pi. So you might understand that why it is coming out to be 4 pi, because of the fact that in this interval 0 to 2 pi, um, this x equal to cosine 2t, y equal to sine 2t is traversed twice. So you are measuring the length of the curve, or you are measuring the circumference of the circle twice. So that's why in that interval 0 through 2 pi. That's why it becomes 2 times 2 pi r, that is 4 pi r equal to 1, because it's unit circle. So unit circle is 1 whose radius is 1. So I will continue with this material in part C of the video. Please watch the next part of the video, part C, concept for section 10.2.